Here in this video, we're going to look at a relationship between the derivative of an inverse function and the value of the derivative of the regular function, or the function that is its derivative. And we'll start with a little discovery exercise here. And so we want to start by graphing the line y equals 2x plus 1. And so I'll start and I'll graph it. So y-intercept of 2, or excuse me, y-intercept of 1, slope of 2. And I get myself some points to use. And we'll connect that with a nice, hopefully straight-ish line. Okay. So what is the slope of that line? Well, the slope of that line is 2. Find the inverse function and graph it. So finding the inverse, we swap our x's and y's. And so we'd have, and try to rewrite it as y equals. So x minus 1 is equal to 2y. Divide everything by 2. And we have an inverse, change color so we can tell the difference when we graph it. Y would equal 1/2 x, and then minus 1/2. So we'd have a y-intercept of negative 1/2, and then we would go to graph, so up 1 over 2. And so we have our graphs there. Now remember, the graph of a function, the graph of its inverse, is symmetric about the line y equals x, and the slope of this curve is 1/2. Now part D, if the point 2,5 is on the original line, so the point 2,5 is on the original line, which is here, so 2, 5. What point does this correspond to on the inverse function? Well, through the process of swapping x's and y's, to find the inverse, the same thing happens with the coordinates. So it should be the coordinate 5, 2, which would be right there. So the point 5, 2 should be on that inverse function, which it is. So if I look here in bold, what we have is the slope of the line at 2, 5 on the original function is the blank of the slope of the inverse. Well, if you're comparing the two slopes, you have a slope of 2 and a slope of 1/2. It's the reciprocal. So it's the reciprocal of the slope of the inverse. So functions and inverses have reciprocal slopes. And the difference is the inverse is calculated using the point I swapped the coordinate around and 5, 2. And that's going to be important for us in terms of how we would do this for more complex functions. Now, the steps for finding derivatives of inverses when I don't have elementary equations to use, you have two options. Option 1 is I can use the process of implicit differentiation. And you start by, you would swap your x's and y's. Now, I don't necessarily have to rewrite our equation as y equals after a swap, but I basically would just swap our x's and y's in our equation. I'm going to swap the coordinate around, and then I'm going to take the derivative implicitly and put the point in, and that would give me my derivative. So you swap the x's and y's in the equation, and then I take the implicit derivative and you turn the coordinate around before you plug in. Option 2 is to use a formula that is based on the composition rule for inverses. And I'm going to derive that right here in our first example. And it's kind of complicated here. This is the way it would read out of a textbook. But I'm going to show it to you what method 2 is through this inverse composition rule for functions. The inverse composition rule says that if you compose two inverses together, let's say f and g are inverses, and after the composition, all you're going to be left with is the original input of x. And if I find the derivative of that, so I do chain rule. Chain rule says take the derivative of the outer function times by the derivative of the inside. is equal to the derivative of x is 1. And so I'm going to rewrite this as g prime of x equals. So g prime of x equals 1 over the derivative of f of g of x. This is that second method I was referring to, where if I had f and g being inverses, g is really representing the inverse function of f in this case. And I have two examples where I want to find values of the derivatives of inverse functions. And we're going to use both methods so you kind of get the gist of both of these. Let me kind of split this in half here. So the goal is to find the value of the inverse's derivative at -1 at the coordinate 0, -1 using both methods. All right. Method 1 is to swap our x's and y's. So I'm going to swap my x's and y's in my problem. And so this f of x would become x equals y to the 5th plus 2y minus 1. Now, when I swap the x's and y's, the coordinate becomes, so my new coordinate becomes -1, 0. That's important. Now I take the derivative of both sides. So I take the derivative of both sides with respect to x. Do my derivative implicitly. So I'd have 1 equals, we would have 5y to the 4th dy over dx plus 2 times dy over dx, and then I'd have minus 0. And we may as well go ahead and write this as dy over dx equals, so I'd factor out the dy over dx. Then divide, and so the derivative of this inverse, without me actually finding the inverse, is equal to 1 over 5y to the 4th power plus 2. There's my derivative expression. To find the value of the derivative, I'm plug in this new point where in my new equation I put in -1 for x and 0 for y. And so the derivative of this, when I put in that coordinate -1, 0, is going to be 1 over 2. So that's method 1 with the variable swap. Method 2 is what I have in green here. So method 2 uses the inverse composition rule. Which I would start with f of g of x equaling x. I would take the derivative of both sides. So that'd be f prime of g of x times g prime of x is equal to 1. Now g is really my inverse function. And so I'm going to divide by the composition. So I'd have g prime of x is equal to 1 over f prime of g of x. And so g being our inverse function here, we wanted to put -1 in for x, because that's what we had to plug in. So I'm going to replace all of my x's in my problem with the -1, and so we'd have 1 over f prime of g of -1. Well, since g is the inverse function, I know that g of -1 is going to give me my original x value. So I'd have 1 over f prime of 0, because inverses, your input in an inverse is technically a y value of a point, and what they output are the original x's. So that's where that 0 came from, was that point up here that had x value of 0. So it's basically telling me that the answer that I'm looking for is 1 over the derivative of f when I put 0 in. So I wouldn't actually have to find my inverse. So we go find f prime. So the derivative of f of x is equal to 5x to the 4th power plus 2. Put in 0, f prime of 0 is equal to 2. And so our answer, 1 over f of 0, we get 1/2. So both ways we get the same answer. Okay, one more example. I want to find, now looking at this notation, the derivative of the inverse when I put 2 into my inverse using both methods. So method 1 is I would swap my x's and y's. So method 1, what color did I use that? I used that for blue. All right, so be consistent. So method 1, swapping x's and y's. So I would rewrite my equation as x equals y to the 3rd power plus 2y minus 1. And then we would take the derivative. So the derivative of both sides, derivative with respect to x of x, and the derivative with respect to x of y to the 3rd power plus 2y minus 1. And we write that derivative line. We'd have 1 equals 3y squared dy over dx plus 2 dy over dx. And then minus 0. Factor out our dy over dx. And we have our derivative equation. So I'm going to come up this way. So I have a little bit more room than I did before. So our derivative expression, dy over dx, is going to equal 1 over 3y squared plus 2. Well, the difference was, in our original problem, we had a coordinate that we wanted to plug in. And so we're asking ourselves, well, what is the coordinate that we would have here to plug in? And looking at what our derivative notation is. Now, this function here, when we're putting in x is equal to 2, this is actually the input of my inverse. So that is actually the input of the derivative of our inverse function, which in terms of the coordinate of f of x means that I have a y value of 2. Now, I need to know, well, what is the x value of this for something down the road? And this is one of those problems that you can kind of look at and tell what would produce a y value of 2. If you put in 1 for the x's, 1 to the 3rd plus 2 times 1 minus 1, that'll make an output of 2. So I really have the coordinate 1, 2. Now, when we do this first method and we swap our x's and y's and then go to plug in, what we do is we have to turn this coordinate around. We make this coordinate 2, 1, where that's the x, and this is the y that we plug in. All right, and so we get that the derivative of this with respect to x is equal to 1 over 3 times 1 plus 2, 1 over 5. So doing method 1, we get 1 over 5. Now let's go through the same process and let's do this again, but using that inverse composition rule to find out what our derivative is. So the inverse composition rule here for method 2 Now, it's good to know both of these methods in case you had to do this with a table and you didn't actually have an equation. The inverse composition rule. So I'd start with f of g of x equaling x and take the derivative of the whole thing. So f prime, use the chain rule of g of x times g prime of x is equal to 1. Now, g of x, or excuse me, g is representing the inverse of f in context of this whole thing. And so since we want to know the value of the derivative of the inverse, we're going to rewrite this as g prime equals. So g prime of x is equal to 1 over f prime of g of x. Well, we wanted to put in 2 into our problem here. So I'm going to go replace everything in my problem with 2's. So g prime of 2, which is really the inverse of f's derivative, it's 1 over f prime of g of 2. Well, since g is the inverse, if I have g of 2 maps me back to a value of 1. So the value of the derivative of g of 2, since it's the inverse of f, is equal to 1 over f prime of 1. So I'd go find the derivative of f. So the derivative of f is going to equal 3x squared plus 2, put 1 in, is equal to 5. So we do 1 over that number, and we have the same answer using 2 different methods.